First question, there we go, it's on the screen. Iron has that density and we have a 500 gram sphere. What's the radius? Okay, so density is mass over volume. So volume is mass over density. Volume is 4 over 3 pi r cubed is mass over density. So that means r cubed is 3 times the mass over 4 pi the density. So the radius is cube root of that. Let's take out the calculator. Cube root of 3 times 7.87 over 4 times pi times, oh actually I wrote the mass isn't 7.87, the density is 7.87 and the mass is 500. Now before I calculate it, let's think about this. How big should we expect 500 gram iron sphere to be? I'm picturing that being quite small actually. Maybe like 1.5 centimeters. Let's see what the calculator says now. Okay, 2.5 about. 2.48 centimeters. Okay, density is mass over volume, so volume is mass over density. 4 over 3 pi r cubed, that's the volume, yeah. 3m over 4 pi, yeah, okay, yeah, that looks fine. Let's pause it and get the next question ready. Okay, next question I have here. How many electron volts are in a kilowatt hour? So I know that 1 kilowatt hour is 3.6 megajoules. Yeah. So let's think about electron volt. I also know that 1 electron volt is equal to, now let me get the constant up, 1.602 etc times 10 to the minus 19 joules. So how many of these are in one of those? It's going to be a lot. So it's 3.60 times 10 to the 6 over 1.602 times 10 to the minus 19. That's 2.25 times 10 to the 25 electron volts. That's how much energy you have in electron volts. That's equivalent to 1 kilowatt hour. Equivalent to 1 kilowatt hour. Yeah, okay. I think that's okay. Actually, you know, sometimes in Google they can do conversions. I wonder if I can for this one. Much to my surprise, you can. 1 kilowatt hour. Yeah, 10 to 25. Yep, okay, great. Let's get the next one ready. Okay, so the next one here, the force is acting on a piece of wood floating at rest. So you've got this buoyancy force and you've got this weight force, and I guess the important thing is to make those arrows the same length to demonstrate that they're equal. Yeah, that's it actually, I think. What else could there be? So next, now state the thermometric property of a thermocouple and a mercury thermometer. So the thermocouple one is the changes in EMF. And then for a mercury thermometer, the thermometric property is the change in volume, changes in volume. So the thermocouple relies on the fact that you get a different voltage between two different metals. If you have two different metals in contact, as the temperature changes, there'll be an EMF produced across the metal bridge, and how much voltage is registered on a voltmeter could be used to calculate the temperature that those two metals are at. And then a mercury thermometer is the one everyone's more familiar with. As it heats up, the mercury expands, and again, this can be used to determine the temperature. So, okay, that's D. Okay. E now, transverse waves can be polarized. Explain what's meant by polarizing. So to polarize a wave means to confine the vibrations and oscillations. I shouldn't really use the same word. Shouldn't really duplicate that. To confine the oscillations of the wave to a single plane. So, to polarize a wave means you'll have your wave oscillating in different directions, but only the oscillations in a particular plane, a particular direction, are preserved. The rest are not permitted. Yeah, I wonder, will Google give any more formal of a definition? Restrict the vibrations wholly or partially to one direction. Yeah, in a single plane. Okay. Let's get the next one. Ready? Well, I guess I don't need to pause. Okay. Well, anyways, let's have a look at the next one. Actually, I don't remember the formula off the top of my head for this, but I do remember how I could work it out. So the idea is you have a sound source, and then 3 meters away from the sound source, you can imagine a giant sort of sphere around the sound source, and the sound energy is spread across this sphere. The area of the sphere is 4 pi r squared. So that would be 4 pi times 9. So that'd be 36 pi. And you have 0.18 milliwatts per meter squared. Let me just get this here into meters. That's 113.097, etc. etc. Meters squared. And you have this much sound intensity. So it's just going to be 0.18 times 10 to the minus 3. That's per meter squared. So if you just multiply it by the area, you've got the answer. So don't really need this number written down. So if I just multiply this by 0.18 times 10 to the power of minus 3, I got the power will equal 204 milliwatts. It's no, sorry, not 204. I mean 20.4 milliwatts. Put my decimal point in the wrong place. You know, that's not... Oh, actually, that is pretty big, because originally it was 0.18 milliwatts and now it's 20.4 milliwatts. Yeah. So as you increase the distance, the intensity gets spread out more. So, yeah, I think that's all fine. I think this is the area for a sphere, 4 pi r squared. 936 pi times milli. Yeah, okay, I think that's right. Like I said, I don't remember the formula, but I think that's right. So this next question here, describe how an insulated metal sphere can be charged by induction using a nearby charging rod. That's actually quite a long explanation. So I just thought it'd be quicker just to reference a website here. This open physics textbooks, I liked it, had a very nice diagram. So it explains, two uncharged or neutral metal spheres are in contact with each other but insulated from the rest of the world. A positive charged glass rod is brought near the sphere on the left, attracting negative charges and leaving the other sphere positively charged. The spheres are separated before the rod is removed, thus separating negative and positive charge. And then the spheres retain net charge after the inducing rod is removed. So that's actually quite a lot to be writing for a short question. And we've got nice diagrams too. There's A and B, and then there's C and D. Oop. Yeah, so as I was saying, kind of a long question for a short question. Yeah. All right. Let's see. Let's look at the next one here. A current carrying wire of length 20 is placed in a magnetic field. When a current of that flows in the wire, the maximum force is that. Calculate the magnetic flux density of the field. What's the formula here? It's F equals Bill. So B equals F over IL. So that's 130 times 10 to the minus 6 over I, which is 55 times 10 to the minus 3 times 0.2. Okay, 130 times 10 to the power of minus 6 over 55 times 10 to the power of minus 3 times 0.2. That's quite small. I should put the answer in millis. 11.8, what's the unit? Webers, isn't it? No, this one is Tesla. Yeah. A current carrying wire of length 20 is placed in a magnetic field when a current of 55 milliamps is flowing and produces a force of 130 micronewtons. Yeah, okay. I think that's okay. All right, next now. What's the resistivity? So the formula is R equals rho L over A. So rho equals RA over L. So that's going to be 2.8 times 10 to the minus 6 times 0.02 squared over, and the length is also 0.02 because it's a cube. So that's nice. Pretty small. 5.6 times 10 to the minus 8 ohm meters. We could probably check the answer by Googling the resistivity of tungsten. .6 times 10 to the minus 8. Nice. Okay, we're getting into long explanation questions again. Yeah, okay. So just to save some time, just try to get some text from the open physics book again. So, basically what's happening here in the Bohr model is you have your nucleus and you have your electrons in orbit, but there's only certain permissible radii. So the electron could be here and here, but not in between. So what's being suggested here is that, by the way, this energy state is lower and this energy state is higher. So if, for example, a electron was to spontaneously drop from a higher level to a lower level, in the same way, like, a book might fall off a table or whatever. Well, what would happen is the electron has lost energy, but because of conservation of energy has to have gone somewhere. So what happens is a photon gets released. And the photon can only have energy that's equal to how much was lost in the drop. And because there's only certain transitions, drops that are allowed to be made, it means that the photon can only have certain energy values, which corresponds to having certain frequencies. So what did it say in this book here? The spectra of atoms produced by electrons gaining energy from source, jumping up to a higher level and then immediately dropping back to a lower level and emitting the energy difference between the two energy levels. So I would have to look up past Leaving Cert exam questions to see how much you have to write to get the full mark. Let's see if I can find it actually. So anyways, I couldn't find it, but I'm sure it would have came up in a past Leaving Cert exam, so you could probably find exactly what you need from a past exam. Maybe if someone knows off the top of their head, they could post it in the comments. The next question was, what is, well, I have it here and I have the picture of it too. So I thought it'd be easier to use a picture than to draw one. What is thermionic emissions? So the thermionic emissions is the release of electrons from a metal surface when it's heated up. And then where does this occur? Let's copy this over. And where does this occur in the X-ray tube? It's on the metal filament. So you can see here, it's this metal filament here. Heats up and it releases electrons. So that's where it happens, on the filament, basically. Filament. And the thermionic emissions is the release of electrons from a heated surface. I think it has to be metal, from a heated metal surface. It's a little bit like there's a photoelectric effect. The photoelectric effect is the electrons are freed from the surface by photons, whereas in the thermionic emission, the electrons are emitted, freed from the metal surface, because the metal surface is heated up and the electrons gain the energy they need to be ejected. Okay. And then let's have a look at the last one here. Okay, so this one here, the electron and positron, the equation for it, I think there's a couple of ways to write it. There's the positron and then the electron, and it comes and it forms a gamma wave. Some people write one gamma wave, some write two. Say a gamma plus a gamma. I think the other symbol is you could have an E, E10 plus E0 minus 1, forming two gammas. Yeah, there's different ways to write it. I think the safest way to write it might be like this, because what's happening is they're cancelling each other out and producing energy. Draw the symbol for the AND gate. Oh, what's the AND gate one? I think it's this one, isn't it? That's the AND gate. Pretty sure of it. And then the truth table for the AND gate. So you have A, B, A, and B. I think that's the symbol. Well, if we use the set notation, I'll just write A and B. Okay. 0, off, 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 on, off, on, off, off, and on. Yeah, I think that's it. Let's have a look here. AND gate symbol and truth table. Yep. Yep. Oh, output. I should have just called it output, shouldn't I? Well, it's not wrong, but I might as well keep it matched up with what most people do. We'll say output. A, B, output. Yeah, okay. I think I've answered everything for that question. Hopefully I didn't make any mistakes. And there you go. That's the general knowledge question for the Leaving Cert exam this year. Okay, thanks for watching, guys.